In the previous video, I blinked the LED by simply turning the pin on and off inside the mine loop, with delays in between. And yes, this works. It works because the microcontroller is doing nothing else. It turns the LED on, waits, turns it off, waits, and repeats. The problem is that this approach only works as long as the microcontroller is dedicated almost entirely to blink the LED. While a delay is running, the CPU is completely blocked. It cannot read inputs, it cannot handle sensors, it cannot react to anything in real time. As soon as you add more code to the loop, the timing starts to fall apart. Every extra instruction changes when the LED is switched, so the blink rate is no longer stable or predictable. You also only get two states, fully on or fully off. There is no real control over brightness, no smooth transitions, and no way to scale this into something more complex. This is exactly why PWM is better. With PWM, the timing is handled by hardware. A timer toggles the pin in the background, while the CPU is free to do other work. The program doesn't have to babysit the LED anymore. It just sets a value and the hardware takes care of the rest. Okay, let's remove this code because we won't need this anymore. And let's add this. We include AVR interrupts to work with hardware interrupts on AVR microcontroller. It provides the ISR macro to define interrupts, service routines, and functions like SCI and CLI to globally enable or disable interrupts. This one provides fixed wide integer types like uint8, uint16, and uint32. It guarantees the exact size of variables, independent of compiler or platform, which is critical when working with hardware registers, timers, and protocols. In this section, I map the hardware registers to readable names. Instead of writing raw register names all over the code, I define aliases for the GPIO port, the timer control registers, the PWM duty registers, and the interrupt related symbols. This does not change how the hardware works, it only improves clarity. If I later move the code to a different pin, a different timer, or even a different AVR, I only need to update this mapping section. The logic of the program stays exactly the same. In other words, this block separates hardware-specific details from the actual program behavior, which makes the code easier to read, safer to modify, and much easier to reuse. This section defines configuration mask for the timer. These macros describe how the hardware is configured, not where it is. Instead of setting individual bits every time, I group them into meaningful masks. One mask selects the PWM mode, another one controls whether the timer is connected to the output pin or disconnected so the pin can be used as normal GPIO. And another mask selects the clock prescaler. This makes the code easier to read and safer to modify. The timer configuration becomes explicit and intentional, instead of being scattered as magic bit operations throughout the program. I highly recommend checking the ATtiny datasheet because all of these configurations are described there in detail. Explaining every single option in a video would take a lot of time, So here I will only explain briefly why we use this specific configuration and not other one. Here we are choosing the PWM mode. We use Fast PWM because it gives a simple, predictable PWM signal with a fixed range and fast response, which is exactly what we want for LED brightness control. You can see here in datasheet the table with the different modes, and this is one we use. PWM can work in normal or inverted mode. The only difference is whether a high level means on or off. This exists so the signal logic can match the way the hardware is wired without changing the code. We have here the normal mode, and here in the datasheet you can see this is normal mode and this one is inverted mode. In both modes everything works correctly, but the MCU pin state no longer directly represents the LED state. In one case high means the LED is on, and in the other case high means the LED is off. This mask selects the timer clock prescaler. Setting CS01 tells the timer to use the system clock divided by 8. In other words, it controls how fast the timer runs, which directly determines the PWM frequency and the overflow rate. Here in datasheet we have this settings, and as you can see we have few other options. Now that we've chosen to use PWM, we need to initialize it before we can actually use it. So this function is responsible for setting up everything related to PWM and timing. The first two lines configure pin PB0 as an output and force it into a safe off state. This is important because the PWM signal will be driving an external transistor, so we want a defined state at startup. The next two lines configure the PWM itself. On the ATtiny13A, PWM settings are split between two control registers, TCCR0A and 0B. So here we set the required bits to select fast PWM mode and the desired prescaler. After that we initialize the duty cycle register to 0, which guarantees that the PWM output starts fully off. Finally, we enable the timer overflow interrupt. We are not using it for PWM generation itself, but as a timing reference. We want to count timer overflows so we can update the LED state and change the duty cycle over time. Now that we have defined the initialization function, we need to actually call it. We add this function call in the main program before the main loop, because it should run only once at startup. Initialization configures the hardware into a known state. And after that, program can safely enter the main loop and start its own operation. AVR has one small quirk when it comes to PWM. A duty cycle of 0 is not always an absolute 0 at the output. In some configurations, the pin can still generate very short pulses, which may cause the LED to glow slightly when it should be completely off. That's why we introduced this function. When the LED should be off, we disable PWM and force the pin to a definite low state, guaranteeing a true 0. When the LED needs to emit light again, we simply reconnect the PWM output and continue normal operation. Next, we define a few variables to track timer overflows and control the LED brightness over time. If we change the LED state on every timer overflow, the LED will toggle hundreds of times per second. In this case, around 585 times per second, which would look like it constantly on. That's far too fast for visible blinking. So, instead of reacting to every overflow, we count them. We only change the LED state after a specific number of overflow events have occurred. That allows us to slow the switching down to the human visible rate. In the first line, we calculate how many overflow events happen in 1 second. In the next line, we calculate how many overflow events correspond to the request number of milliseconds. Thanks to that, we can control the blinking speed in real time. For example, if we pass 500 milliseconds, the LED will toggle every 500 milliseconds. If we pass 1000 milliseconds, it will toggle every second. Next function ties everything together and sets the initial parameters for blinking. It receives the desired brightness and the on and off times in milliseconds, converts these times into overflow ticks, and stores them for the blinking engine. We disable interrupts to prevent inconsistent updates while modifying shared variables. Then we reset the overflow counter and the current state, and force the LED to start in the off state. Finally, we re-enable interrupts and let the timer-driven logic take over. Now we just have to add this into the main function, so it will set up everything on the startup of the MCU. The last function we need to understand is the interrupt service routine. This is a special function. Its header must look exactly like this, because it is connected directly to the hardware interrupt vector. This function is executed automatically every time a timer overflow occurs. We don't call it manually. The hardware does. At the beginning, we increment the overflow counter. This counter represents how much time has passed in terms of time overflow events. Then we check the current state. If the LED is in the on phase, we compare the overflow counter with the required on duration. When the counter reaches the value, we reset the counter, switch the state to off, and force the brightness to 0. If the LED is currently in the off phase, we do the opposite. We wait until the counter reaches the off duration, then reset the counter, switch the state to on, and restore the configured brightness. So this interrupt routine acts as small state machine driven by timer overflow events, and it is responsible for switching between on and off at the correct time. And one last small thing, we have to turn on the interrupts in the main function. So we have to add this here. And that's it. Our program is finished. Now we can save this, build this, and upload into the ATtiny. If you don't know how to program ATtiny with Arduino Uno, check out my previous video where I am showing how to do that step by step. Now we can finally move on to our actual device. First, we will remove everything that was directly related to the NE555. I will speed this part up so we don't waste time on mechanical steps. Now we can connect our ATtiny. Let's insert it somewhere here. Now let's connect VCC to the ATtiny, pin number 8. Next, let's connect the ground, pin number 4. And let's connect our pin number 5 to the base of the transistor with 1K resistor. And the last one, the capacitor 100 nanofarad between the VCC and the ground. And now we can turn on our device. And now you can see the device is working properly. In the next video we will make the second mode, fade in and out for LED, also using PWM.